Thank you, Lore. Okay, yes, you can hear me. I
Yes,
can.
yes.
So, thank you for inviting me. It's my pleasure to be here. And as Lorenzo was mentioning, we know each other since university. We studied together. So, yeah, exactly. So we did the university together, and we ended up both like here in UK. So today, I will try to give you more a general perspective of the philosophy of the research I'm doing that is connected to robot learning. Let's say there will be part in which maybe we will dive in slightly more in the approach, and others instead that help to give you the big picture, let's say. But of course, if you have any question, please interrupt me, and feel free to have a session that is interactive as much as possible. So, I mean, you know that we started robotics with something like this, where robots were designed to avoid as much as possible physical contact, physical interaction with the environment. And mainly in this context, as you can see, there was no humans in the loop, sensors were mainly inexistent, and the environment was really, really controlled. And robots were mainly programmed to do a single task. But of course, we moved very far from this, and now, I mean, we are seeing, and you are studying that with robot learning, I mean, we can achieve very incredible capabilities that before for robots were simply a dream. And so you can see not just in manipulation, but in locomotion, and in general in dynamic behavior for control. However, today, what I want to pose you the attention on is, despite this, there are still situations in which robot learning still breaks. And we can still see failure, especially when contact is not sensed, because the robot cannot adapt to the physical world. And so is not able to deal with uncertainty, and this leads to incorrect force application. So, and maybe inability to perform certain tasks. So, of course, without accurate content information, the robot operate with an incomplete understanding of the world. And in the context of my research, I've started to look at, to try to solve this problem, to how biological organisms, human, instead deal with this uncertainty. And if we look at this, what we can see is physical contact is definitely embraced. We have bodies that are not rigid, but they are soft. But also, we can really rely on our tactile perception, our sense of touch. So what we will look towards this lecture is actually how I'm trying to take these hints and, let's say, look at providing robot with the capabilities to safely interact with the environment, sense it, and be able to, let's say, enable this physical interaction. In this respect, my journey started with, let's say, the design of artificial skin, very, let's say, in the past, so when I was doing my PhD. And the idea was to provide the whole robots with the opportunity to measure interaction forces. This was a sensor that, is very simple in the idea because it was using capacitive transducers, so the same technology you have in your phone. And we were actually designing it as a sort of triangular mesh, mimicking the idea of, let's say, the 3D graphics, such that we could conform it to different robot bodies. With this type of sensor, what we could achieve was to measure 1,000 of contact points along the surface of the robot. And this is what more or less is the response of the robot. So, of course, the resolution is not very high, similar to other tactile technologies that at the moment are used for fingertips. However, like what I can tell you is that in our body, we don't have the same spatial resolution everywhere. And for sure, like what we need to feel in our fingertip is not the same as we need to feel in our back, for example. So we were trying to find a compromise here, to trying to, like be able to have a spatial resolution that could enable, for example, detection of the hands, and we will see this like in a second. But let me come back to this video. So you can see that like you can still have an idea of the shape of the hand and stuff like that, but still with the resolution that was computationally not too expensive, let's say. Of course, having this kind of information enable the robot to safely interact with the environment, and in this case, like this robot has artificial skin covering the whole black part, and is not having any prior information of the environment, and is not relying on cameras, but is exploiting the distributed information provided by this artificial skin to be able to control the interaction forces and, let's say, accomplish the task of reaching in different parts of the environment. This is not robot learning, it's classical control approaches, so this actually just to let you put this like in the broad framework, but what we were developing here was to have a task priority controller, so it's a sort of controller that in which different tasks have different priority. You have like a priority task in this case was to control the interaction forces, and the secondary task was actually the reaching task. And so we could, in this way, with this architecture, enable this sort of safe exploration in this cluttered environment. But also, as like in this case, I was saying like this enable human-robot interaction. Here you can see that, again, the robot is covered here with the skin. Here you can see the response of the sensor that like are this sort of the tactile image, we call it tactile image, that show more or less the hand of the operator. And we could exploit this to control the robot to be able to perform certain tasks, again, guaranteeing safety in this collaboration between the robot and the human. Here we used a little bit of learning. What was interesting is that we tried to learn like to recognize the gesture of the human operator and use it for controlling the robot to perform different action. And what I wanted to pose the attention here was that, of course, one of the problems is that gestures are quite dynamic. So if you have like some sort of, let's say, torsion or like a tap, or so these are like dynamic gestures. However, from the actual tactile images that you can, for example, see here, like some gesture cannot be distinguished if we look at them as in a static manner. So what we do was to actually augment this input with a sort of dynamic information, and so we were able to, with the optical flow, to be able to add also this change over time of the contact that was happening. And so these two input together, like provided with the convolutional neural network, was actually enable us to be able to recognize different gestures that later we used to control the robot. I want to pose another attention here on the fact that of the embodiment. So this robot is very geometrically easy in the sense that these are all, let's say, cylinder, okay? More or less of the same shape. But there might be body of robots that are quite diverse. And so the same contact, the same gesture in different part of the robot can generate a different type of tactile image. And so, of course, like it becomes very difficult to, let's say, generalize towards like different robot parts or body parts, okay? So because of the embodiment role. In this case, let's say that it was more simple thanks to the geometry of the body. But to enable safe interaction and physical interaction in dynamic environment, of course, it's not just being able to monitor when the contact is happening, it's also providing robot with spatial awareness, maybe observing the contact before it even happen, and combining these two information. So what we did, this is something that in our body we do by combining proprioception and vision. So what we did in this case was to extend the previous artificial skin, providing with the distributed little eyes around the body. The reason was because we wanted to enable the robot to have sort of spatial awareness without relying on external cameras. So imagine that you want to deploy this in the environment, you cannot necessarily rely on external camera mounted in the environment. So you want the robot to be able to have this spatial awareness. And the other aspect is we didn't want to have just a single camera position in a strategic point, because of course this might lead to some case to occlusion. Sorry, was looking for the word. Instead, by distributing this information all over the body, we could actually augment the visibility, and also we could use it as a sort of proximity sensor. So we could actually monitor when a human operator around or any other object was approaching the system. Here, what you can see, I'm sorry, maybe it's not very clear, but here, this kind of distributed sensing that are actually time of flight sensor are providing a point cloud of the environment, and thanks to that, the robot can have information of, let's say, the geometric feature of the environment around it. This is just to give you a little bit of more information of the type of sensor. These are if you have familiarity with LiDAR, so these are imagine tiny LiDAR, okay, even if it's slightly different, the field of view. However, they have very low resolution compared to LiDAR. So there is, and also they are quite noisy. But again, as I was saying before, we need always to find a compromise between the resolution, because this means computation, and we want to close control loop that potentially are reactive control loop. So we need to actually have and think about that. Thanks to this sensor, what we did was to actually enable robot to perform self-localization, for example. So having mapping the environment and after relocalize itself. In this case, what we did was to develop a probabilistic model of the sensor and use it applying classical Monte Carlo self-localization algorithm. So here another interesting aspect is that we were starting to combine both information coming from these little eyes with the information from the tactile. And so here you can see that the red point cloud are coming from the time of flight, the green dots belongs to contact that happened between the robot and the box. Again, we were able to control the interaction forces, but this also was used in this algorithm to actually support the localization. And I was telling you also we were using to perform motion estimation. So if you want to enable collaborative work, you want that the robot is able to estimate the velocity of an object or a human approaching and react accordingly. So we needed to be able to let's say, estimate this from the point cloud coming from the time of flight. It was not easy again, because this kind of sensor, as I was saying, are quite noisy. We needed to combine information for multiple sensors and project them in all the same space. And so here we were using a sort of ICP algorithm, but we had, in a way, to even if the algorithm is a classical algorithm, we needed to preprocess slightly the information to be able to achieve this result. learning means that we need to, as I was saying, combine information coming from different sensors, because like we want actually to have not just information about the geometry of the object, but how their physical property, that is what touch provide us. And we were working to, like similar as it happens in our brain, we were trying to find out a way to integrate the two information in a single representation. When I say representation here, and because you are doing learning, I'm not talking about latent representation at this level yet. I'm just talking about encoding both information in the same sort of data structure. If like this, I call it representation because like for me, we are representing the information through, in this case, a point cloud where the color channel is used to encode information of, for example, the stiffness of the material. But like this is not a learned representation. So potentially you can use this to learn something else and have at a later stage a later representation maybe of something different. So in this case, what we were doing, I was saying, was exploring objects and trying to, as I said, encode also their physical property within this point cloud representation. And that is because, again, you might have let's say, bottle of water, but the geometry might look like the same in two different objects, but they might be, let's say, very different when you try to manipulate them in terms of their physical property. And so we wanted to explore this. So we were actually exploring the object, assigning the different the different points of the point cloud, the estimation of the compliance of the robot, and this was enabling, for example, the opportunity to, again, based on that, control our interaction forces. So if you have something that doesn't give you from the visual perspective of information of that, but actually have different mechanical property, you can control the robot to adjust its force to avoid that, to squeeze the object. And also, you can use it in a different way. So imagine that, like, if I'm relying only on vision, and I see this situation, I might calculate the distance between these two objects, and evaluate if my end effector is able to pass through without any unwanted collision. However, in the moment in which I have information about the actual mechanical property of the object, that I can encode in this representation, what I can do is to exploit this and take decision such that the robot can, for example, I think like that is at the end, is here, just to speed up. So it's actually pushing towards the object that is more soft, this one, to be able to pass through. So this is, again, to combine these two information. And of course, like multimodality, is something we should look at also in robot learning. There is, however, like a problem related to tactile. So for robot learning that was based on camera, we can rely on a huge data set, ImageNet. And so, we have a lot of data. We can train as much as we can. For language, we have the entire web. And so, again, we have enough data to use all these transformer and so this kind of architecture that are data angry. However, for tactile, this is like more difficult. And that is, in my opinion, one thing that is limiting, in this case, the use of this technology slightly in robot learning. We are getting there, but I will tell you this like in a second. So the idea is that why is difficult? It's difficult because tactile data sets are difficult to scale up. So we don't have ImageNet for tactile. The reason is because the sensor, contrary to cameras, like we have so many different technologies available. So we have data that are in theory technology specific. Also, tactile is multimodal. some sensor maybe provide only certain type of information, but there are also sensors that can provide multimodal information. They are actually dependent, so it's very different. So we don't touch statically, guys. We touch in an active way. Touch actually require our embodiment to get in contact, and also depending on the type of action we do, we might get different type of information of the object. Imagine here you have a table, and maybe you want to just feel the texture on the top. You lose your finger and you just slightly rub the surface. And these go to stimulate certain type of mechanoreceptor. If I want to understand something about the, let's say, compliance of this table, I stiff my finger, I push down. I want to understand its temperature, I just leave my hands like this. So there is the action affect your perception. And so this is actually something that again make this different too, because in theory you should have acquired data also depending on the action you do. And finally is also spatial dependent, as I mentioned before. So you can have the sensor in different, embedded in different parts of the body, and the same type of contact might lead to different type of maybe tactile images or information. So finally, it's time consuming compared to camera. You can, with the camera, get easy the information of this object. Tactile require you start to so provide you local information. So if to have the whole information of this, I need to touch many times. And by the way, because it's a physical contact, probably I have to do it controlling also the interaction forces to avoid to destroy the object. So you can understand that this is a huge problem. And so people started to look at, okay, how can we solve this? And part of the business is that we had the new type of tactile sensor that is based on, let's say, cameras, that is camera-based tactile sensor that in some way, in my opinion, are getting traction also because of, let's say, they are in a way also overcoming, besides the huge spatial resolution, but I think that they are also, let's say, be more closer to how we were processing data for images, and so people are exploiting this. What we did was to, let's say, develop a method that was exploiting nerve. I don't know if you know what it is, and it actually is able to, from an image, reconstruct the 3D shape of an object, and it does this by looking at how the light is actually reflecting on the object. So it's if you have multiple images, you can actually reconstruct the 3D object. And we were using convolutional GAN. So what we did was, first of all, to avoid to have to collect the data physically on the objects. What we did was to exploit the simulators. And the reason why, and the first simulators we had were actually for camera-based sensor. So that's the reason why we started with this, because it was convenient. So it was also already there. And this in particular, we were using Digit, is a sensor that from Roberto Calandra and Facebook that has been designed. So what we were doing was to actually explore the simulator to be able to collect and train a model that was relating RGBD information on the simulator and tactile information from the simulator of the sensor. And after we were exploiting NERF to be able to, given a certain position in the object, actually generate the corresponding tactile image on that object. So actually we could, for example, say, okay, I would like to know in this object what is the tactile response if I touch in this point. And so using NERF, we could actually check and generate the data for that. So this is like actually give you a little bit of more information. So after training NERF on different type of object, we could actually query the pose, generating a corresponding visual image in that position. This was given to a trained convolutional gun that was the one that we trained in simulation between the RGB image and the corresponding tactile image. And so we could actually generate the corresponding image in the tactile sensor. So these actually give you also some results like for the similarity score. So of course we were looking if the actual generated image were similar to what we would have achieved in the real world by touching the object in certain point. And we got good result. And thanks to these methods, what we could do was a sort of zero-shot methods, because we could train everything in simulator, and without any further, let's say, exploration in real world, we could actually transfer to real world. Another aspect here that I was trying to achieve was the fact that when we touch, as I said, we wanted to be not dependent on the orientation of the sensor. And so again, we try to achieve that, but also we wanted to, let's say, be also resilient to certain fault. And so we were conditioning the training to actual the background of the sensor. For example, if you know how this sensor works, they have some sort of LED, so with the color, and in some cases maybe some of them can be broken, so you have a slightly different background. If that happens, of course, you might not be able to generate the correct information. So, oops, sorry. Let me check. Why is? I try with this.
Maybe it's going to sleep.
I try to. No, I mean I was.
It disappeared suddenly, not when you touched.
Let me check if I can end and try again.
If you want to put this, then we have to.
Sorry, about it. Yeah. Okay. So this is actually something that you can see here, where so if some of the LED is broken, you might have a different background, and so we were actually conditioning to that, so we could actually be also resilient to that, and also we were in the training again, taking care of the fact that we could have touching the object with different orientation. So this, from my perspective, was a way to try to start to generalize with respect to this condition that usually were not seen before in literature, in other approaches. Another important aspect for me, like I told you, that the problem of translating. So I mean, if I get a data set with a certain sensor, what happens if I have a different sensor now? Can I reuse that or not? And so again, this was something that I was investigating. Actually, this is quite old work. It took a while to get it published for some reason. People were not understanding probably when I proposed it. But the idea for me was, okay, what if I collect my data set with this digit, and now I wanted to reuse it if I use this is two triangle of the technology I showed you before, and that was integrated on a fingertip. Of course, what you can just already see is that the difference between the spatial resolution of this sensor versus this one that is quite coarse. But what we were trying to achieve here was, and here we are talking about latent representation instead. We are learning a tactile geometric spatial representation. So both these sensors are actually providing this information, but they are encoding them differently, I mean, with two different tactile type of image. And so we are trying to learn this aspect. and being able to transfer from one to the other. In this case, like, it looks like quite complex. In reality, the first things you can see is that this sensor provides with information like a sort of array. So you have that each tactile element provides with a value that varies over time, depending on the pressure that you are applying. And this, because it has a camera, provides straight away with an image, okay? So what we need to do was, first of all, to translate this array of value in a sort of tactile image. And here we were encoding also the spatial relationship between the tactile element. So, of course, as they would be pixel in an image. So, okay. And when we have that, what we can do is start to actually be able to relate the two information and learn this common representation that encode, for example, geometric aspect of the contact. And this means, like, for example, edges or surfaces, smooth surfaces, and so on. So here, after, like, we were using these pix-to-pix to perform that, and after we were taking back the information to the original type of the taxel-based tactile sensor. So the other things we were trying to, so I had this idea and I said, okay, in doing this, like, I'm not interested in learning different objects because I want to generalize. So how I can do that? And I was thinking, okay, I can actually learn the tactile primitives. What I was saying, like, we were trying to look at type of tactile primitives and use that because we were thinking in general objects we might be able to recognize this tactile primitive. Each object might actually have edges, smooth surfaces, and so on. So what we were looking here again was to try to train using this and learning our representation using these tactile primitives, and after trying to see if we could generalize to unseen object later on. So this was the main idea towards this work. Coming back to the original storyline, I told you that beside tactile, that of course is like very something that, like, I'm working on since my PhD. I've started also to look at the aspect of the embodiment, and now we look at how the embodiment also has a role in our perception and might have a role also in robot learning. So before to go on, like, I want to focus again on the biological bodies and compare them to the actual bodies that we can see in our robot. And first of all, like, biological bodies, like, differently from rigid robot, like, they actually exploit nonlinear dynamics. So, for example, the arrangement of in the eye here, like, is able to compensate for parallax effects, but also the way in which the spider uses the spider web is an extension of his body in terms of perception, and, like, the morphology of the web and the type of thread that he uses. It used, like, actually transfer vibration in different way, giving, like, the spider the exact position of the prey. So this is actually to show that here nonlinearity is exploited, and also body morphology simplifies control. So we are used to robot learning everything in the brain, and but I mean, I think, like, you can understand that this is not really scalable. Certain point, like, I mean, we are like we need huge computational power. We want our robot to last in the wild for long, and they are usually using batteries. So you understand that, like, there is quite a problem. So until you are in your office and programming, oh, fantastic, and the robot there, fantastic. In the moment in which you want to deploy something around, this might not so easy. So in this case, like, as I was saying, like, body morphology simplify also the control. So this actually is called the dead trout experiment. Here, this you can see the actual movement of the trout that is placed in a flow water. And if you would not know that is that, you probably would think that this is a fish that is swimming. These actually demonstrate how the body in biological organism has been shaped by evolution to fit their ecological niche perfectly and actually to solve some task. That trout doesn't have to really think about swimming. The body is already performing that task. And so the philosophy here is that part of the controller can be implemented by the body itself if designed in a good way. But also the other aspect is that, like I will show you in a second, so with robot learning, what we are looking is like to make our robot very intelligent. But intelligence is distributed in biological bodies, I was saying, can also emerge from the interaction between brain, body, and environment. So these actually explain it very well. So before, we are used to a certain paradigm in robot, that is the sense, think, act. Here, we have this part that is the body morphology actually have a role in our perception and intelligent behavior. And of course, in this, that's the reason why I'm working on these things, is because it's strictly related to touch. And let's say our intelligence develop through the fact that we physically interact and they use this sense to understand the physics of the world. How I approach this for robotics, I read looking at manipulation, simply because hand is very fascinating and it's a difficult problem in robotics. We have more than 100 years of people trying to make hands. Of course, now again, we are seeing incredible hands, but I was interested here more in understanding this aspect of how the embodiment actually affect my perception, my tactile perception. So what we did was to actually try to design a hand that was including softness, compliance, but also a little bit of structure. So here the mechanics of this is not completely soft. There are some structural aspects. But also I was trying to integrate a tactile sensor in a monolithic way. So trying to print the system with already the sensor in it, because I wanted that actually they were part of the embodiment itself. So these are sort of chamber that are filled with air connected to barometric sensor. So of course, when you press, you can measure the pressure, that is the difference between the internal pressure. In this case, is not is atmospheric pressure and the external pressure that is when you are in contact. I was not very interested in the let's say high spatial resolution here. I was more interested in exploring. So what I wanted was the whole hand with the sensor, because I wanted to explore the adaptability and the embodiment. So of course, we 3D printed it, and you can see that thanks to this compliance, even with a simple control, so just connecting all the actuator together and making just a simple open-close open loop, so you can actually be able to adapt to different objects quite nicely. The end could be controlled with all the different degree of freedom, but in this case, again, I was trying to explore more its morphology and compliance together with the tactile sensing. These actually show that anyway we were trying to, in some way, to replicate some aspect of the morphology of the human hand, in particular the kinematics. And the idea for me was, okay, usually when you try to recognize object with the rigid hand, you need also aspect of proprioception. That means the information of the posture. You need probably to plan how to grasp and so on. Here, what I wanted to explore was that thanks to this compliance, what happens is that you have, so the embodiment is actually have a role in how these tactile sensors are activated when we get in contact with objects. And so here what you see is like the different color correspond to the pressure that is measured depending on where we touch the object, similar to when you actually put your hands in your bag and try to find the keys without looking into it, okay? And we wanted to be able to recognize these objects, and for doing this, we actually developed this architecture, and we implemented it in a sort of Bayesian way that is similar how we do. Like, imagine again, your hands in the bag, what you start is like, you started to touch, you get some information, you have a belief of the object that you have in your bag, and maybe you retouch again, and you collect another belief, and these actually, like, together with the information you get from your tactile sensor, and like goes to change, update your current belief, and in this way, at a certain point, when you are like you have reached enough confidence that the object that you are touching is what you're looking for, you can pick it up. Does it make sense? Okay. So this is actually more or less roughly what we were trying to implement. So here, these are the information from the sensor that were distributed in the hand. And again, these are like, imagine an array of value, each element corresponding to a different sensor, pressure sensor. And this is actually your belief, your probability distribution. And this is like fed back together to the current information when you touch again to update this belief. So this is actually more or less what we were trying to achieve. And this is like the type of architecture. So what I wanted to like make you like focus on is that, first of all, touch is so like in this case a spatial there is a spatial information that are important, something that we try to achieve by so these are like the different tactile input, and what we did was to actually with this part of the architecture, like obtain a sort of like matrix embedding that was actually encoding the spatial relationship between the different tactile sensors. So that is because when you touch, of course, that information already like is important to relate the output of the sensor together in relation to the embodiment. So where the sensor are placed in the embodiment. So, and we were using, like, again, a convolutional neural network to be able to identify different type of feature. And here at this level, you can see the recurrent neural network that was the part in which the information from the current touch were like combined with the previous belief to update the current belief and be able to, let's say, recognize the object. So here you can see, right? So the first touch, you have a guess, and continue to touch, and you start to like update its belief until like you recognize this is the cup. Thanks to this architecture, so first, like as I said, why we were using this type of architecture instead of transformer or so first of all, because coming back, the problem of data-hungry architecture. We were not in the position to collect enough data as like that kind of architecture would use. Secondly, because convolutional neural network in this case, like we could exploit the spatial information that actually was encoding aspect of the contact, and so thanks to that, like we could do this like with the less complexity possible, let's say. Going forward, I don't know, like stop me, Lore, because okay. Going forward, like I told you that the control can be, in a way, part of the control can be implemented by the body if the body is designed intelligently, okay? And so I started to work on design optimization methods, like especially when you have a soft robot. It's not very straightforward because we don't have like a long history of robot design, and so like the first let's say approach was like by intuition, trial and error. But what we want to do is to be able to instead design system that actually enable us to design the right body for the actual task or the ecological niche where we want to place our robot in. So what we were doing here, like this is a specific case, so we were actually looking at shape matching. So imagine that you have like a sort of tentacle robot, soft arm, and you want that arm to achieve a certain shape. What we were trying to do was to design this system in which we were, first of all, exploiting finite element simulation to collect data that were used to train a surrogate model. And this surrogate model was used through a bi-level Bayesian optimization, achieve like the kind of morphology of the body that was enabling us to achieve a certain shape. Okay, so imagine that you want your tentacle to achieve this shape. Okay, what we did was to let's say design or divide this tentacle in elements. Each element is parameterized and so can change this sort of size of this convolution or like some material inside, the placement of the material and its compliance, so you can use more rigid or more soft material. We use finite element simulation to actually like simulate what is the response of each element, depending if we change the material, we change the geometry, or so spanning the whole design space of the parameters we have available. When we have this, we train our surrogate model with ANN, and in this way, we are like not anymore relying on a type of simulator that is computational expensive, but we can actually just use this to use by level of Bayesian optimization and get to, let's say, the design of this tentacle such that by just inflating with a single input, we could achieve the desired shape. And what I can do is show you the result. Okay, so this is because like we find out for each of these elements where to place some sort of, we call it constraint, so material that are more rigid in certain part of it, and like changing depending on the shape. You can see some are like small, large, and so on. So part of, let's say, of learning is also like learning a model that enable us to understand the behavior of such system, and so we can use that to design intelligently their body. We also expand this a little bit more, like this, to actually, instead of doing a single task, what I was trying to achieve, this is not published yet, we submitted. So the students has to graduate, so I hope that like they take it. So what we were, the idea, I told her, look, we cannot do just a single task because like we want to have a system that, depending on the task, we can just get the right body. How can we do that? Then this, like the task may be manipulation, gripper, but can be also, let's say, more tentacle or like in future locomotion or stuff like that. So what we were trying to do here was a similar approach where we were trying to, let's say, learn the model of different, let's say, element of these potential robots. And so given an input, what is the corresponding output? We are still, and we were not focusing only on pneumatic here, we were also using a tendon-driven system. So we were trying to also generalize, like in terms of the full framework to actuator were not just pneumatic. But what we were doing was to actually learn a meta model. So instead of just trying to learn the relationship between the design parameters and the surrogate model. So in this way, we could actually generalize. And later, we could exploit reinforcement learning with PyBullet to actually find out what was the best design to accomplish a certain task. And this is like the sort of, so there we were trying to evaluate is what we got in simulation was actually successful in real world. So we printed this and we were testing with different objects. And we were also adding extra weight and so on to check the result. I was saying like that it was like quite, so we were trying to also evaluate for other tasks, like this was the shape matching, so I don't know why the videos are not like running right, but the idea is like that we were also being able to, let's say, learn models that were robust to gravity and so on. That is usually something that is very different between, so it's a sim to real problem, more or less, because you still have this, and we were trying to, let's say, overcome aspect of sim to real, because like you can definitely get a design from the simulator, but when you actually translate it in the real world, like this might have issue. This also has been extended in a different, let's say, scenario, in the idea of this optimal placement of sensor and optimal morphology of the sensor. So you know that tactile sensor requires, so these actually are pressure sensors, so, but in general, like they require a sort of deformable layer, so the material of that layer affect the perception, act as actually as a low-pass filter, depending on its mechanical property. The area that you are covering with it, so these are aspects of the morphology of the sensor, but also like their placement within a certain structure. So what we were doing here was to have a data set collected with at the gate lab of a person that was working on a pressure map, and based on that we could actually optimize the sensor placement and the morphology of this soul that is part of the sensor, because it's the embodiment in which the sensor is placed, and so it's affecting its perception, and that this like lattice structure can again geometrically change to change the response of the sensor. And we were actually placing the sensor, not uniformly distributing them in the soul, but placing them exactly where was needed to be able to reconstruct the pressure distribution in a good way without overloading like the aspect of like power consumption and computational aspect that, of course, like you usually for wearable system you have like very limited computational capabilities locally. So we were trying to do something like that, and I mean this was like the let's say the 3D printed soul, and so you can see that these are the response of the sensor while it's actually walking in different terrain scenarios. So what we are investigating is, of course, this can be also in your robot, of course, like where I place my sensor, like in the hand or like in the body, right? And so you might include, this is actually what we are working on, the whole, not just the actuator, and but also the actual sensing in the body. This is what we are working right now. Okay, so takeaway of all of this. First, like for me, physical interaction is essential for learning by experience, and in general, like so if we want to achieve intelligence, we need to like make the robot able to actually take information from the real world. So like robot learning, also in simulator, reinforcement learning, like are definitely important, but I think also that we need the system be able to gather as also information with physical interaction. And so these require us to design system that can do this safely. This might achieved by designing robot with the soft body, adaptive body, and also providing them with the sense of touch, because like even when you have very limited spatial resolution or like fewer sensors already, these provide a lot of information that you can use, and so definitely important, in my opinion, to be able to actually learn better from the environment. Even if it's a seminar, but these are all the students I had, postdocs I had so far since I opened up my lab. So, and of course, these are the people that like, do the work. And so, of course, like thanks to them that take my crazy ideas and try to make them real. And thank you again for listening to me. I hope it was not too boring, understandable, and yeah, open to questions. Good.